morning and good afternoon, everyone. Welcome to this webinar series with Curtis Whitson about water hydrocarbon PVT. My name is Mohammed Dahouk, and I'll be having the pleasure of moderating this webinar. I'm CEO for Whitson, based out of Norway. Before we get started, we'll just go through some meeting logistics here very quickly. We have over 300 registered participants in this webinar, and therefore we can't have everyone talking at the same time. So we're using Teams for the webinar, and everyone is muted by default. That doesn't mean that you cannot ask questions. Actually, there's a specific part of the talk that is supposed to be a Q&A at the end. So please ask your questions in the Q&A chat box within Teams. The session is supposed to last between 45 and 60 minutes, including the Q&A session. And very important, we are actually recording here, so that you will be receiving the recording. If you registered for the webinar, you'll receive the recording after it's finalized. And a reminder that this is the webinar is facilitated by Whitson. We're basically a company that commercialize different software and do consultancy worldwide. Some of the software that we commercialize is going to be presented here, like Whitson Plus. It's basically a web-based application that allows you to do DCA, PVT, bottom pressure calculations, numerical modeling, all this for unconventional multi-frac horizontal wells. We also have a software called Whitson PVT, which basically is one-stop shop for everything related to PVT, and where some of the technology that Curtis is going to be presenting in this webinar will also become available very soon. And then we also have Whitson Academy, which many of you who are present here are subscribers to, and that's basically our hybrid learning platform where you can attend both live courses and live webinars like this one, and on-demand pre-recorded courses. For anyone who wants to look at the different list of courses that we offer, both software related and also technically related to PVT, gas EOR, or unconventionals, you can go to whitson.com/training, and there you'll also find a list of our upcoming webinars. We have webinars already lined up for next year, and you can also watch the recording of previous webinars from the same place. Whitson.com/training is the URL. Just a kind reminder for those who would like to participate in our yearly conference. It's held in Houston, Texas. It's basically hosts around 150 to 200 people, different engineers. And if you're interested in attending WhitCon 2024, just send an email to my colleague GM Americas, Carson at whitson.com. With that, I'll just jump over to introducing the speaker here. It's hard to kind of really do justice to your bio here, Curtis, but I'll do my best in one slide. It's basically Curtis has a bachelor's from Stanford in 1978, and then he came to Norway at NTNU, the Norwegian University of Science and Technology, where he completed his PhD. On the professional side, he has been for many years and is currently still a professor at the Norwegian University of Science and Technology here in Norway. He's also the founder of our company, Whitson, which previously was called Pera, and also the founder of a previous software company called PetroStreams. He's actually also the creator and the developer of different software packages. One of the main known ones is PVTX, that it was sold and now is commercialized by another company. Multiple publications throughout Curtis's life. You know, one of the most known ones is the SPE Phase Behavior Monograph, basically the go-to book when it comes to phase behavior for petroleum engineers, or from the Society of Petroleum Engineers. He has also a book with Mike Golan about well performance, and multiple published papers and different publications. He's also a recipient of different awards from SPE. One of the most recent and most renowned ones is this the Anthony F. Lucas Gold Medal from SPE. And most importantly, actually, is for myself, he's a long-term friend and big mentor, and it's a privilege to be able to work with Curtis. So with that, Curtis, give the floor to you. You can share your screen and your camera and turn on your audio. There we go.
Okay, thanks, Mo. Appreciate that introduction. And yeah, I've got see if I can do this right. You know, all the open, put that down. Yeah. So thanks for joining those who are actually made it of the 300. And we are going to talk about water, hydrocarbon PVT. This will include actually some non-hydrocarbons, important ones, CO2, nitrogen, H2S. But we won't talk about things like IFT and hydrates, which are important, can be important, and just not going to be covered here. Yeah, basically all the associations Mo went through. Just get straight to the topics going to try to cover in this 45 minutes. The summary, water hydrocarbon phase behavior. I'm going to kind of go through the key elements of Chapter 9 in the SB phase behavior monograph, the things that are really the core to, in fact, I'll talk a lot about laboratory measurements made starting during World War II in the early 1940s. And then basically are still equally valid and being used. Most of these were converted into correlation equations, well or early, however, but they were converted into correlations and being used still in most of the software that's around. I'm going to talk something about the concept of saturated and undersaturated water. This is particularly important to understand and differentiate for systems where an aquifer is in place and active in the recovery performance of a hydrocarbon reservoir, but also for the situation of CO2 sequestration, for example, where the initial aquifer would be clearly undersaturated. It is becoming saturated with the injected CO2. I'm going to talk about some work that we did back in 1992 on doing EUS modeling with an aqueous phase and how to do accurate predictions of how the components, non-hydrocarbons and hydrocarbons, partition into the aqueous phase, be it a brine or fresh water, and as well how the water component partitions into gas and or oil or the non-aqueous phase. For example, CO2 and sequestration. So how much water moves into this CO2 phase or into a hydrocarbon reservoir phase. Solubility, mutual solubilities, basically, and then the volumetric properties of those phases, how they change where you include the effect of water. And then finally, there's some challenges that really haven't been resolved in the industry, and this in particular, oddly enough, is how well or actually how poorly the equation of state predicts the volumetrics, in particular, the compressibility of the aqueous phase. It's particularly bad, and we have some ways to go about actually fixing that problem. So I'll just show some examples of that at the end of the presentation. Want to remember some folks, trying to do this every time I teach and hold a webinar. These are folks that are, some of them, I guess in this case, I believe all of them have passed. The original paper, 1944 by Dotson and Standing. I don't know some of the dates of birth and passing for all the folks here. I couldn't find them online, but these are the most important papers, and they're regarding water hydrocarbon phase behavior. Culberson and McKenna. McKenna and Wee is also a very important paper on the water solubility in natural gases. Wee Bigatti on CO2. Kobayashi and Katz did some very important work early on as well, back in the early 1950s. I just want to remember these folks, and if you've got some dates on some of these people that I wasn't able to find, I appreciate. Unfortunately, I only met a few of these folks. Dr. Standing, who was a teacher I had at Stanford, Dr. Katz, who I had the fortune of meeting at once. Otherwise, these are people I don't know personally, but should be recognized for their contributions. This is just an example of different types of brine that we have We've got seawater here, basically around 35,000 parts per million of these, what we call solids that are dissolved in the water, about 35,000 parts per million. If the maximum you'll find before the salt that stops dissolving in the water is around 350,000 parts per million. Here's actually a Kansas Wilcox Reservoir, which is at the brink of precipitating out salt, more than likely. Probably a lot of salt in the well bores of producing wells from this field. 350,000 is about the maximum salinity, and then everything in between as well. Some gas and oil reservoirs have brines that are less salty than seawater. So these are just some examples of Rune Field is here, and so forth. These are just examples, and basically it's not just sodium and chloride, sodium chloride salt, but that's usually the majority of this what do you call these folks? Ions, or yeah, that make up the salt in brine. So basically, there's a lot of different ways to define the salt concentration. We got mole fraction is, to me, the most intuitive and natural to use, but most people don't think in terms of mole fraction. You got weight fraction, molality, molarity, parts per million on a weight basis, part per million on a volume basis. There's a lot of ways to get confused in this world. And papers dealing with water and brine will use a variety of these. Okay, so just so you're aware of them. And there's some equations in the chapter 9 that kind of give you a way to migrate back and forth from one definition to another. And some of those definitions require the density of the brine itself as a function of the pressure and temperature, and that's given here in an accurate correlation by Rowe and Chow. And they give a correlation for brine densities as a function of pressure and temperature for a wide range of sodium chloride solutions, and up to very high pressures and temperatures. And this is just this simplified version of that applies at standard conditions. This is probably this is the most important paper. It's the most comprehensive paper dealing with the pressure, volume, temperature, and solubility relations for natural gas water mixtures. This was by Dotson and Standing. Like I said, I had Standing as a professor at Stanford, and I was there 74 to 78. And I think he came to Stanford in 73, just after he'd spent 2 years at the university here in Trondheim, starting the Department of Petroleum Engineering in 72 and 73. That was after an illustrious career he had working only for Chevron after graduating from the University of Michigan, originally from Utah. So they put together and made measurements. I'm going to actually read this little abstract because it tells you kind of what they did, and it's fairly short and concise. So they present pressure, volume, temperature, and solubility data for mixtures of natural gas and water, and for pure water. When they say water, they're talking about pure water, and for mixtures of natural gas and 2 typical oil field brines, stating that these data permit estimations of the solubility of gas in reservoir interstitial waters and of the amount of water vapor present in free gas phase of the reservoir. Compressibility and formation volume of the gas saturated interstitial water are given as function of degree of gas solubility. Investigation covered pressures from 500 to 5,000 psi, PSI-A as we call it now, temperatures from 100 to 250 degrees Fahrenheit, which were at the time the range of reservoirs, petroleum reservoirs, and then the water or brines having up to 35,000 parts per million total solids. Now, summarizing the results of the paper in one sentence, basically, some of the results it is stated that the solubility of natural gas in connate or interstitial water may be an amount of about 20 standard cubic feet per barrel at 5,000 psi. Doesn't sound like a lot compared with the solubility of gas and oil. Now, the solubility of natural gas in brine decreases as you get a more salty brine. Compressibility of the saturated liquid phase increases, in this case up to about 20% at 5,000 psi, with solution of 20 standard cubic feet of natural gas into water, barrel of water. And the amount of water in the gas phase is dependent on pressure, temperature, and the salinity of the brine from which the water was vaporized. And what I want to make it important is that they basically made measurements. They quantified the measure of order of magnitude for all of these key dependencies of the properties that are needed to do reservoir engineering. So that's basically their work, and I'll show you some of the natural gas that they looked at. It's mainly containing methane, of course, ethane, propane, and they had two waters, two brines, fairly low salinity. One almost the same salinity as seawater. I'm not sure if it is seawater, probably not, but and then one with a little bit lower salinity. These are some of the key relationships for solubility of natural gas and water. We've got basically in standard cubic feet per barrel, we got this maximum up here around 20 to 25 standard cubic feet per barrel at 5,000 pounds. The variation with temperature for a given pressure. And they also give the correction term to this solubility, or this is natural gas solubility in pure water. So if you've got a salt or a brine, basically it tells you how much lower the salinity will go for a given amount of salinity in the brine. And that varies somewhat as a function of temperature. So you got all these main dependencies of, and we call this solubility RSW, same as RS, but RS typically is the dissolved gas in an oil. This is dissolved gas in water. And it's related to the mole fraction in the water phase of the gas component, of the natural gas component. So you can go back and forth between standard cubic feet per barrel and mole fraction with this very simple equation. This gives the basically the formation volume factor of water as a function of pressure, and the solid lines are for pure water. Okay, so it's pure, basically pure compressibility effect, and we all know that, of course, the pure compressibility factor is going to decrease the volume of the water. If we add fully saturated gas, basically that formation volume factor will change, and the increase in the compressibility will change accordingly. Now, the interesting thing to notice about this is that these are all, the dashed lines represent saturated water, okay? And we normally think about saturated oil having a formation volume that decreases with pressure, right? That means as gas comes out of solution, going from 5,000 pounds to 4,000 pounds, you've got less gas in solution, and we normally expect that oil volume will shrink, right? Because of the gas coming out of solution. But here you've got two effects going on. You've got the compressibility effect of lowering the pressure, and you've got the loss of volume due to the loss of material, the solution gas. So in this case, it's the compressibility effect that dominates. So we actually get basically a increasing water volume as the pressure is decreasing, which is obviously different than for oil. But this dashed lines are saturated water. The solid lines are pure water without any gas in solution. They also converted this into a compressibility table shown here. Or basically, we see water compressibility usually considered around 3×10 to the -6 as a rule of thumb. For water compressibility, here you can see its dependency on, for a saturated water, basically its dependency on pressure and temperature. Excuse me, this is for pure water. Down here, we've got the effect of the solution gas oil ratio on that compressibility, increasing it up to as much as 20% for this pressure range of 5,000 psi. So these are all the properties for the aqueous phase that they measured and presented in clear table forms. On the right side, we see the solubility of water, pure water, in natural gas. Now, if you've got basically a very, a brine with a lot of salt in it, and you equilibrate it with natural gas, methane, natural gas, whatever, what you'll find is that none of the salt ions will partition into the gas phase, negligible or zero. So what you get dissolved into the gas phase will be pure, potable, drinkable water. And I remember Dr. Stander used to say is that whenever you go out in the field and he wanted to know whether a gas well was producing any free water, which could lead to, precipitation, salt scaling in the well bore. He would just get a sample of water from the well separator and drink it, taste it. Maybe he didn't drink it, but he'd taste it. And if it was just dissolved water in the gas, and if it's freshwater tasting, then basically he knew that there was no free water being produced from the reservoir. So this basically gives the dependency on temperature, strong dependency on temperature and pressure, and a bit on salinity for how much water dissolves into natural gas. Now, in 1951, some years later, Culberson and McKetta, and if you're a UT graduate, the department, I think, of chemical engineering at UT is called the McKetta School of Engineering, if I remember right. Basically, they made measurements of methane solubility in pure water. They went up to 10,000 pounds and to much higher pressures than did Dotson and Standing. So this is a curve that's has a wider pressure and temperature range than the Standing data, but it's for pure methane. Now, way back in 1940 and 1941, Wiebe and Gaddy, apparently Gaddy was the guy making a lot of very unusual high pressure and temperature equipment, laboratory equipment, measured the solubility of CO2 in water. And who'd know that, close to 100 years later, that would be such an important issue in today's CO2 sequestration that's going on worldwide. Now, just to give you a perspective on how much more CO2 dissolves in water than natural gas, this was the maximum solubility, the 20 cubic feet per barrel Dotson and Standing measured for natural gas, primarily methane, at 5,000 pounds. And basically, you can see up here, we've got 160 to 200 standard cubic feet. So almost a factor of 10 times the solubility of CO2 in water as natural gas. Okay. Another interesting feature about the solubility of CO2 in brine and water is that will normally lead to a water of a higher density than the water with no CO2 dissolved in it. Okay, so the CO2 saturated water density is typically greater than pure water density. Okay, it's just a kind of a curiosity, but so CO2 is behaving very differently than natural gas when it comes to water. These guys made the measurements back in 40 and 41 for pure water and looking at the effect of salinity. You can see the effect of salinity will reduce the solubility by about a factor of 2 for what would be a quite salty brine, 180,000 parts per million. Still much higher than solubility of natural gas. The McKetta and Wahey paper in 1958 is one of the most important, basically water hydrocarbon papers that are publications around. I think I'm not sure exactly where the original 1958 paper came, but it came into petroleum engineering literature, I think, through one of the first handbook of petroleum engineering back in early 60s. But basically, they measured the water content in methane and natural gases, and so they basically, this chart gives the barrels of water dissolved in 1 million standard cubic feet of methane as a function of pressure and temperature, much like the measurements of Dotson and Standing. But they give correction for the salinity, can't hardly read this, for both the gas gravity being, in other words, there's no correction if it's pure methane, but as you get to heavier and heavier gases, the solubility of water decreases with this correction term here, which is also a function of, I think, temperature. And then they also give the correction term for brine, the loss of solubility of water if the water is a brine and not pure water. And the correlation between this solution water gas ratio and stock tank barrels per million standard cubic feet and the mole fraction of the H2O in the gaseous phase in the reservoir is through this very simple relationship. I remember when I was at Stanford, Dr. Ramey, Hank Ramey, was teaching the natural gas engineering course. And he said if I was ever to be thrown onto a desert island and had to do engineering consultancy by myself on a desert island, there'd be one book that he needed. And that book was the book by Kraft and Hawkins. He said, that's a book that I would like to have to do my reservoir engineering. But he noted that in that book, there was basically only about one major error. And it was this particular figure that was in the Kraft and Hawkins book. I'm not sure exactly how it got translated and that it was not correct, but he said you don't want to use that chart in that book for designing your surface facilities and water handling of gas fields. Now, I'm going to talk about the concept of saturated and undersaturated water. Reservoir water, connate initial water, or aquifer water can be classified basically into two main categories, either saturated water or an undersaturated water. And first, we're going to talk about saturated. So saturated reservoir water or brine is any aqueous phase that is sharing pores with a non-aqueous phase or phases. So if a pore in the reservoir doesn't contain a non-aqueous phase, namely gas, oil, CO2, if it only has water in it, okay? Then it's potentially going to be undersaturated. But if it shares in the same pore, if the aqueous phase shares the pore with any other non-aqueous phase, gas, oil, CO2, whatever, then the aqueous phase will be saturated by definition. By saturated, we mean that the aqueous phase in the pore is fully saturated with every component found in the non-aqueous phase or phases. That is, it's in thermodynamic equilibrium, is existing between the aqueous and non-aqueous phases. That means there's no more of any component in the non-aqueous, let's say oil phase or gas phase, it's fully saturated the aqueous phase with all components, methane, CO2, C1, C2, C3, etc. Now, the non-aqueous phase component distribution in the aqueous phase. So the components that partition from the non-aqueous phase into the aqueous phase will be dominated by the lighter components, all the non-hydrocarbons, particularly CO2 and H2S, and the light hydrocarbons. And it only contains smaller amounts, if not negligible amounts, of the heavier C3 plus components. Okay, so the component distribution in the aqueous phase looks very different than the component distribution in the non-aqueous phase. Okay, so that's just something that is generally the case. Now, a reservoir water that is undersaturated will A, be any aqueous phase that's 100% saturating the pores, but B, that the aqueous liquid phase is at a pressure above its bubble point, which means that if you take that water and you lower the pressure, you'll have no gas, no light components coming out of solution. Now, where will we find undersaturated water or brine? There's basically two places. In the aquifer, at some distance from the contact, oil water contact or gas water contact, because at the contact, the water is sharing pores with the gas and or oil, right? But away from the contact, below the contact, the process of diffusion will obviously saturate some of that water below the contact. But if you get far enough away from that contact, you'll start seeing that the water contains is only partially saturated, or what we call in an undersaturated state. Likewise, for shale zones that are interspersed within the reservoir rock, could be fully water saturated. Okay, and at the boundary where the shale is in direct communication with the reservoir rock, the water in that shale will be fully saturated. But within the shale zone, if it's thick enough, there may be parts of that shale water that do not contain or that are undersaturated with respect to these lighter components. So basically, the properties of undersaturated water are only needed either in the aquifer or within the shale zones between the reservoir rock. Now, how do we model with an equation of state? How do we model the aqueous phase? Okay, the effect of the aqueous phase on the non-aqueous phases, or the effect of the non-aqueous phases on the aqueous phase itself, on the water. So it can be done with a cubic equation of state, and the paper that we wrote in 1992 in Fluid Phase Equilibria, Ingo Soreda and myself, used the Payne-Robinson equation of state to basically, we took all of the laboratory data that existed, some of that I referenced early in the presentation, all of the mutual solubility data that existed in the literature at the time. We basically tried to come up with binary interaction parameters that would allow us to get accurate prediction of the light non-hydrocarbon hydrocarbon components in water and brine, and the amount of H2O that partitioned into non-aqueous phases like gas, CO2, natural gas, and oil. And to do that, based on people who had looked into using a cubic equation of state at the time, there's just a few people who had looked at that. What they found is that if you used one binary interaction parameter between water, H2O, and all the other components of around 0.5, value of about 0.5, then any cubic equation of state would then predict the water saturation in, for example, a natural gas very accurately. Basically, 0.5 was the number. So if you wanted to get the amount of water dissolved into methane or CO2 or whatever, or maybe not CO2, but the hydrocarbons was around 0.5. Okay. But then looking at how the different non-hydrocarbon and light hydrocarbons dissolved into pure water or brines required a completely different and sometimes negative binary interaction parameter to get the solubilities of the non-aqueous components into the aqueous phase. So basically, if you want to get the aqueous phase composition, so I think I've gotten this. Yeah, so the Kij aqueous basically is getting the composition of the aqueous phase right. So that would be the non-hydrocarbons and light hydrocarbons, the I there, correctly predicted as a function of pressures, temperature, and salinity. And then for the non-aqueous phase, getting the solubility in this non-aqueous phase, the composition of the H2O basically in that gas or oil or CO2 phase. So it's the second one, the BIP should be around 0.5 for the hydrocarbons, but for the aqueous phase, getting the solubilities in the water phase was much more complicated set of BIPs to get that. So you have to do two flash calculations in order to get the composition of the brine phase correct and to get the composition of the non-aqueous phases correct. Now there are other methods using, for example, where you can do a single flash calculation using something like the Huron-Vidal mixing rules, but I'm not going to go in and talk about that. Some of the software in the industry uses that approach as well. But with this first approach, you can basically, with two flashes, get compositions of both equilibrium phases accurately by doing two flash calculations. Now, the first thing we got to do is, if it's a brine, you need to modify the alpha term and the A constant of the cubic equation of state to get the water brine component vapor pressure predicted correctly. So this is a plot of vapor pressure versus temperature. The 0 is pure water, and the 30 here is about 300,000 parts per million. And if you get to higher saturations of salt, basically you start getting a solid phase. So this is how the vapor pressure curve changes for different brines of different salinity. Now, using this modified alpha term, which we give in the paper, if you take this is the reduced temperature of the water component, this is the salinity. If you use this alpha term in the Pang-Robinson equation of state, then it will predict basically this set of curves almost exactly. Okay? So it'll change the vapor pressure of the brine according to its salinity. Now, the VIPs we're talking about, if you're talking about the hydrocarbon phase, which would be the non-aqueous phase, and we've got these Kij values, which we call it for hydrocarbons, but it would also include nitrogen, CO2, and H2S. If you're interested in getting the flash calculation that gives you the amount of water component in the if you want to get the water component in the non-aqueous phase, right, then you use this A. If you want to get the nitrogen, CO2, H2S, and light hydrocarbons in the aqueous phase, right, then you use this binary interaction parameter for the aqueous phase, for the two different flashes. So here you see that the Kij equation for the non-aqueous phase calculation to get the solubilities in the gas and or oil phase accurate. So you can see it's a function of the reduced temperature of whatever component you're looking at. Salinity is shown here with the CSW. And basically the coefficients A0, A1, and A2 are given here. A0, A1, and A2. And then you've got the capital A0, A1, and A2 are functions of acentric factor of the component. For nitrogen, CO2, and H2S, we've got different relationships here. So basically, you have to decide which component you are looking at, and you get the BIP to use for the flash calculation that will give you the correct composition of the brine phase with all of these components partitioning into it. To get the water content in the non-aqueous phase, be it gas or oil, we just need to use these constant Kijs. You see they're all around 5 for the hydrocarbons, 0.5. And then for nitrogen, close to 0.5, CO2, 0.19. And for H2S, there's a slight temperature dependence. Okay, so basically we have to do a flash calculation with these BIPs if you want the composition of the water right, solubility in the water. You need to use these BIPs in a flash calculation to get the water content in the either gas or oil phase. So these are some examples from the paper showing the use of these correlations with the Pang-Robinson equation state, comparing the symbols, which were experimental data. This is for the methane water system, pure water system of solution gas, gas-water ratio. So this is the solubility of methane in water as a function of pressure and temperature. Again, this is just a different expression for the same quantity. This is the mole fraction of natural gas in the water phase, okay, as a function of pressure at 100 degrees Fahrenheit for the two different brines considered by, actually for pure water and brine B, considered by the Dotson and standing one. This is at 150 Fahrenheit, 200 Fahrenheit. This is again the solubility of nitrogen in water and brine. This is pure water here. Different brines here. And as a function of this, the mole fraction of the nitrogen in the water phase. Lines being the equation of state, Pang-Robinson equation of state with these BIPs, and the symbols being measured data from different authors. This is basically the water H2O content in the natural gases of the Dodson standing looked at, that natural gas composition I showed you, between 100 and 250 degrees Fahrenheit. And this is the mole fraction of the water in the vapor phase. So the question is, that was in 1992, and basically for mutual solubilities, for most petroleum systems, and in fact, even for looking at sequestration and so forth, this method can be used for estimating the component mutual solubilities. But the problem was that in our practice, we didn't look at it and didn't talk about it. How accurate does it measure density, or does it calculate the density of the brine phase, for example, and compressibility and viscosity? Let's do it on time. We're getting close. So I'm going to show you an example here. This is brine density. This is at this is for, I think this is 25,000 parts per million, 237. This is for one of the clients we have. We did these, they had some measurements, and then basically what you can see is that we got brine density, and we're off by only 0.3% at 10,000 pounds and about 0.5% in the other direction at atmospheric conditions. Now, in general, we look at that kind of density error and we say that's fine, right? Less than 0.5%. But the problem is that if you translate that into compressibility, which is very important for aquifers, what you see here is that you're off 20 to 30%. Same equation of state, and basically this is the data, or this row correlation, which is really kind of an ultra accurate brine, sodium chloride brine correlation. So this is the type of error that we're getting using the equation of state. We're getting good solubilities from this method with the BIPs, but we're not getting good compressibilities. Okay, so the question is, how or can we do something to improve? Well, the densities are okay for gravity, gravity transport, segregation in the reservoir, whatever. This kind of density accuracy is fine. But for the compressibility effect, which obviously is important both in terms of aquifers and sequestration, being off 20, 30, 40, and up to 50% is not good enough. So we've developed a new method. It can be used actually with any cubic equation of state, not just Peng-Robinson as mentioned here. But the new method's been developed to ensure accurate water, brine, liquid properties from any cubic equation of state and the LBC correlation for viscosities. And how that's done is that we, depending whether it's pure water or brine, we use the NIST for pure water, or we use the Rowe-Chow density correlation, and either NIST if it's pure water, or the Keston correlation for sodium chloride brines, to generate what we call water brine data at a specific temperature and salinity. Okay. So with those correlations, we know we're within just, small percent of laboratory data for brine and pure water. Okay. We then do this modeling with Peng-Robinson or the SRK equation of state to fit these data. Okay, I'll show you the kind of accuracy that you can get. But then you have to be able to get the solubilities right. Okay, with this modified volumetric equation of state here. So how do we do that? So what we do is that the aqueous and non-aqueous BIPs to use with this new equation of state treatment here for the aqueous phase volumetric properties have to be redetermined, and they're done automatically so to match the accuracy of the original Hays Whitson Peng-Robinson EOS method predicting mutual solubilities at the specific temperature and salinity of the brine with non-aqueous phases containing any of these hydrocarbons and non-hydrocarbons. Okay, so we create data from the original Serrated-Whitson method for compositions of the brine, compositions of the non-aqueous phase, and we find the new BIPs with this new treatment of the volumetrics to match these mutual solubilities. And the result of that is basically shown here for the same example, okay? So now we're plotting density versus pressure, where the deviation is like 0.00x%, okay? Basically line thickness difference between the two. But if you look at the compressibility, you see it's spot on with this new treatment of the equation of state. So the special tuning Taylor-Robinson equation of state gives you both the densities and compressibilities accurately, and a set of binary interaction parameters, aqueous and non-aqueous phases, that ensures that you get the same degree of accuracy you got with the original Serrated-Whitson method, which did not have, which had basically the original Serrated-Whitson method was giving these kind of volumetrics for the aqueous phase. So we haven't published the method in its entirety, but basically this is just showing some of the results, and this is included in our Whitson Plus software currently for systems and tight unconventionals where the water treatment is important. So I think with that, a little over time, but not too much. Stop for answering any questions that you folks may have.
Yeah, thank you very much, Curtis. This is great. So we got some questions here, and you cannot unmute. Just a reminder to everyone that it's not possible to unmute, but you can write your questions in the Q&A box or in the chat. So the first question, Curtis, is when is accounting for water in our PVT most important, and when is it not?
Okay. Well, taking account of water for aquifer pressure support clearly can be important in some reservoirs and not in others. So in general, the water compressibility, the accuracy of the water compressibility will be very important any time the aquifer is either large or you have a high pressure, even if it's a limited aquifer. So high pressure and limited aquifer, or large aquifers where there's a lot of pressure support coming from the aquifer. So getting that water, aquifer water compressibility accurate is important. CO2 sequestration, important because basically you stop sequestering CO2 in an aquifer when the pressure reaches a certain level, okay? When you can't inject enough CO2 into the aquifer. So for limited aquifer sequestration, then clearly getting the compressibility of the water, be it undersaturated and or saturated, and it'll be both in that situation. Getting compressibility right will control how fast you reach that limiting increase in pressure in the aquifer. If you're looking at natural gas production and you need to design water handling facilities, then of course having that water content in your production stream, your well stream accurate is important. That's a situation where you need accurate prediction, including the water. In terms of gas oil systems, develop miscibility, compositional gradients, the effect of the water phase on dew point, bubble point, two-phase volume splits, it can generally be ignored. In general, and that's what we do in petroleum modeling, reservoir modeling. So it's generally speaking not important for getting the gas oil phase behavior right. Okay. So definitely CO2 injection either from petroleum reservoirs or aquifer sequestration would be important. Surface calculations important. And you also have the special case where you get salting out around gas wells. Basically, the water you can get scale solid precipitation usually in the well bore because of the you get a little bit of flow of brine into the well bore, and you get all this undersaturated gas entering the well bore as well, and then basically it will absorb all the water and it'll desalt the water, and the salt will start accumulating in the well bore. So that's another potential important area.
Yeah, thanks. Thanks, Curtis. The other question is, I think it's kind of related to this, probably to the CCS application. It says that how does the presence of impurities in hydrocarbons such as sulfur or mercury or other heavy metals influence the brine solubility? If you have any ideas of models that are available to account for that, if there is an effect.
So brine solubility in water solubility in like a gas, or solubility of components in the aquifer?
I think it's probably brine solubility in the gas. Or
Water
water
solubility in the gas. Yeah, well, actually, it doesn't really matter in either situation. The effect of mercury, what was else? Was it mercury?
Sulfur.
Sulfur on mutual solubilities? I have no idea. I have no idea. I've never really dealt with a problem where it was, whether there's laboratory data out there, maybe not. If not, then probably should be measured, but I don't know, actually.
Yeah, very good. There's a question about if the water viscosity correlation that is in the SPE phase behavior monograph, if that's in line with the Keston correlation that you've mentioned here, or if that's different.
It's not probably in line with the Keston. I'm not real sure about what that water viscosity correlation would be. I can just look real quick here and jump to the Keston is an ultra accurate correlation. I just don't remember if that's what's given in the monograph. Here. Maybe up here. Yeah. There we go. Yeah, Keston. It is the Keston correlation. Yeah, it looks like it is the Keston correlation, if that's what they're talking about. And now some of the coefficients given there could be errata. You need to get the original paper, probably. Do you remember, Ahmad, when we implemented it, we done all the testing, we compared with NIST?
Yeah, I think it's was
okay.
Okay.
Okay. Yeah, you can go to NIST to check this correlation for pure water. It's good. They're very, very consistent with each other. But this correlation also works for salinities up to 300,000 parts per million sodium chloride. So yeah.
And just the last question here before we have to wrap up. When it comes to being able to actually model this, there's a couple of questions about if you know about reservoir simulators that have the capabilities to model water CO2 issues, or if you know of either reservoir simulators, or if you think you have to do some special treatment to the PVT to handle it appropriately.
Reservoir simulators to handle CO2, probably CO2 sequestration type. Yeah.
Yeah.
Yeah, there's Yeah, there's probably a lot more out there than I know about, but the Eclipse 300 has some has the treatment, I think, more or less what we're doing here for the solubility, neutral solubility, probably mainly the CO2 solubility and the brine is treated with, I think, the method we have here. It doesn't correct this compressibility problem, but that could be probably introduced to using Eclipse 300. Dave Ponting, who developed Eclipse 300, has been working the last, I think, 4 years on basically a CO2 sequestration simulator that's open sourced, that is available to basically download and use for free. And I always get it pronounced wrong, and he'll shoot me if I say it. Open Go Sim, or
I think it's Open Go Sim.
Open Go Sim. And both Dave Ponting is heavily involved in that, and he's expanding that from the CO2 water only to also handle the hydrocarbon full three-phase capability now. So if you want to do sequestration in depleted oil and gas reservoirs, that can be done. I think so. That's obviously a very interesting one, since it's basically open source. It's, you know, you can download it, you can use it. I've got some graduate students using it. They got some nice, I think that's certainly less expensive than Eclipse 300. So, and I think there are some other, I don't know whether they're free or open source, but other models specific to sequestration being developed. But at least that's 2.
No, that's great. Thank you very much, Curtis. Thank you everyone for attending, and we will be sharing the recording of the webinar with the slides sometime in the upcoming days when it's ready. Thank you very much, everyone.
Pleasure. Take care.
Bye-bye.
Bye-bye.
Okay, Curtis.
Yeah.